I want. Like it's NP complete and it's like there's no good algorithm for it. And just in general, what's his name? Ethan Holland. He said he did his SRP where he was having to check. And like, you know, even once you get up to like, I don't know, 15 or something vertices, it's like becomes like just impossible to like run these programs, which check to see whether two graphs.
Once you get past like, once you get to like 11, it takes more than an hour to run it on a normal computer.
Yeah.
When you hit like 15, it takes weeks.
It's just gone.
Wait,
it's just gone.
Right.
You just can spend months checking if two 15 vertex graphs are isomorphic. It's like there's just
The
no algorithm.
exponential growth of the algorithm just takes off after 10 vertices.
It's like worse than exponential. It's like factorial. It's like I don't know.
Wait, factorial is it?
I don't. Not exactly.
Yeah.
Like no.
Yeah.
Nine vertices took about an hour for me and Robert Fleischman
You did
to
this?
do over the summer.
Oh, you did this last summer?
Yeah, with Robert Fleischman.
Oh, cool.
Like,
Oh, 2 summers ago.
No, it was
Last
summer. Ours was not with Ethan Hall.
Oh, okay.
But ours was like similar to that. Like 10 vertices were okay. 8 vertices took like 10 minutes, and then 11 took like a day to run. And yeah,
What were you actually checking on these vertices?
It was like spanning trees. It was similar.
Yeah.
Depth first search.
But generally, yeah, but when you want to check all possible cases of something, you don't want to spend time rechecking isomorphic cases. And so like there are just tons and tons and tons of graphs which are actually just isomorphic. But before you can rule them out, you need to know. Anyway, this is really, really hard. And there are very few actual sort of theorems that we can mention right now because it's just hard to do. You can check the number of vertices, you can check the number of edges, you can check that the matrices have certain properties, you can check the degree sequences, but then you're just, at some point, you're just like kind of screwed.
Wait, Mr. Rose?
Yo.
So by like Stirling functions is like n to the n in terms of complexity, but I think there's a random algorithm that you can make where like you take one of these and you multiply by some like randomly generated elementary matrix that like swaps in rows and columns. And you check it, like you subtract from the.
Yes, there are like what's it called? There are like
Heuristics for checking.
yeah, they're like sort of like algorithms that like 99.9% of the time will tell you whether they're isomorphic by like actually doing things. What's that called? What do you call an algorithm which is like approximately correct, probably very, very likely correct? What's the name for that?
Not a heuristic.
I need to know more math.
Wait, it is a heuristic.
Good. All right. So good. That was a beautiful conversation. New topic. Up here.
Or random algorithms.
Rotate the camera.
Critique.
Wait, critique. Hang on, critique.
These two graphs that I meant. So these two graphs which I mentioned earlier. These two graphs which I mentioned earlier are over there. I will redraw over here. Suppose I give you a graph. It is just V, E, and V. V might be just having 4 points, A, B, C, and D. And the set of edges might be A, B, B, D, A, D, A, C, and B, C.
Is there an optimal?
That's the way. Stop talking. And that's all. No, one more. No, that's it. Okay, so we have been kind of casual up until today about just drawing this graph however we want. And we have been sort of basically just associating, the picture with the graph. But when I go to draw a graph like this, I see, okay, well, there's a couple different ways I can do this. So I don't know, I can put A, B, C, and D over here. If I do that, I get A, B, A, C, A, D, B, C, and that's it. No, one more. B,
D.
D. So that's a perfectly nice graph, and I'm quite happy with myself. But I could have, as we talked about at the beginning of class, drawn this same picture totally differently. And if we are, so yeah, So same exact graph, and yet they kind of look a little bit different. In particular, the striking difference between these two pictures is that in this picture we have edges crossing, and in this picture we don't have edges crossing. And so this property of edges crossing or not is not an inherent property of the graph. It is a property of the representation of the graph. And this is called a representation, a sort of pictorial, graphical, geometric representation of the graph. It's called an embedding. So this is one embedding, and this is another embedding. This is a so-called planar embedding. And this is a non-planar embedding. A planar embedding is one in which you just do not have edges crossing, except where they meet at actual vertices. And we like these. Which graphs are planar and which graphs are not? Which graphs can you draw without having any of the edges cross? All right, question over there, or should we keep going? All right, so there's this famous kind of sort of house and utility problem. I think someone said that you guys had learned about this, like in middle school or Puzzle Palooza or
Definitely,
something.
it's very famous.
Very famous. Okay, so suppose you have a house. This is the house where Jamie lives, and then you have another house. This is the house where Anna Barth lives. Give her an extra window and no door. And maybe like a zip line to a tree. That's how she gets home. And another house where I live, and so it's like, you know, I have a chimney, so that's cool. Okay, good. Now we have some utilities. What?
Santa Claus.
Exactly. We have some utilities that we would like to connect to. So this first utility is like, maybe this is like, you know, gas. And maybe the next utility is like water. And now let's have a silly one.
Sausage.
Whipped cream.
Wow, GG.
Good. Alright, so everyone needs a supply of whipped cream. How else are you going to get your whipped cream except turning on the whipped cream spigot in your house? All houses in the future will have this. It's an important public utility. It's regulated, etc. Okay, can we connect these three houses to the three utilities? Well, if we try to do this, like I can connect Jamie's house to gas, water, and whipped cream, he is good to go. But then if we start to connect Anna Barth's house to gas, water, and whipped cream, we see that the lines are crossing. And now it gets even worse. Once we get to my house, it's just like, oh God, all these utilities and they're all crossing each other, and all the gas, water, and whipped cream lines are all getting crossed. You don't want that for obvious reasons. All right, how can we fix this mess? What can we do?
Consider it with 3D.
Put water on the other side. Yeah, that's a good idea. All right, so he says put water over here. That like starts to solve the problem a little bit, right? Now the water and the gas lines are not crossing, but the whipped cream line is still crossing. What can we do? Where can we put the whipped cream?
In between those two gas lines.
Like here?
Yeah, why not?
Okay.
We lost the whipped cream
Oh, we did?
Yeah, we
to
did.
the first house.
Okay, if this is whipped
Wait, I
cream,
didn't know that there was one.
no, everyone needs whipped cream.
Oh, okay.
Can we get whipped cream to my house?
Yeah.
Yeah. Can we get whipped cream to Anna Barth's house?
Yeah.
Can we get whipped cream to Jamie's house?
No.
Somehow this whipped cream line is always going to have to cross. All right, so famous problem. Okay, what is this graph? Of course, this is just K33.
Yeah.
The complete bipartite graph, K33. Okay, so theorem, K33 is not planar.
It's like how many
And what does that even mean? That means that there does not exist an embedding of the graph K33 in which the edges do not cross. All right, and if you kind of have this theorem is going to be different from all of our sort of other theorems of graph theory, because this isn't even so much totally about graph theory. This is about the particular embeddings of graph theory. In other words, it's about geometry. So this theorem is going to sort of transcend graph theory, but also geometry. We're going to have to be talking about lines crossing, and if we want to get really, really technical about this, it would be hard, right? We'd have to have sort of various axioms. Which, if you've been hanging out with Gabe at all in the last 2.5 years, this is what he's devoted his entire life to. It's just like drawing lines and shapes over and over and over again, seeing if they cross each other. So this is what it's all about, right? And we need some quite fancy geometry theorems. Like if you took logic with me last semester, you might know about these fancy 20th century like axioms which say that every line, separates a plane into two half planes in such a way that if you have a point in one half plane and a point in another, that the segment connecting them must intersect the line creating those two half planes. So like things like that, which are kind of common sense and no one bothered to even like state formally until a couple hundred years ago, those things are all going to come into play. We're going to do this kind of informally. Shall we begin?
Yeah.
All right, so theorem K33 is not planar. All right, so let me just get a nice little picture of K33. Here's ABC, here's DEF, and here is what this graph looks like. Right, this particular embedding is certainly not planar. What I need to prove is that no possible embedding can be planar. So I have to, as I construct this, like consider all conceivable embeddings, okay? And I'm going to be slightly hand-wavy about this, but it's going to be a lot of casework. All right, so for step number 1, let's just take some of the points. And let's just like get those down on paper, and then we'll worry about adding the other two in such a way. Okay, so if I am going to have A, B, D, and E, already, as drawn, they're like not planar, right? So there's really only one way to draw these 4 vertices in a way that they're not planar, and that is to make a square. Okay. So the argument rests on that. If anyone would like to challenge me, do so now. Let the record show no one challenged me. So okay, good. So A, E, and then we'll put B down here. And I'll put D here. Okay, so A is connected to D and E, and B is connected to D and E as well. This is essentially like the 2-house, 2 utilities problem. And so if we have no whipped cream and we just have 2 houses, of course it is possible to do it by just putting the gas and the water on the opposite side of the houses, as just discussion. Okay, good. All right, now note that this cycle produces 2 regions. I have now decomposed the plane into 2 regions. There's a region on the inside and the region on the outside. And so I'll call this region 1 and I'll call this region 2. And basically, what can I say about these 2 other points, C and F?
They either have to be in region 1 or region 2.
They either have to, intuitively, they either have to both be in region 1 or both in region 2. Because the 2 more points that I have to add to my embedding are themselves connected via an edge. And by the very nature of the geometry of the situation, if I put 1 point on the inside in region 1 and 1 point in region 2, well, by these like kind of plane separation ideas, which are common sense but also need to be stated by someone at some point, any line connecting C and F is going to cross through one of these edges which I have made, and so that's what's not allowed. So I either need to put both points outside or both points inside. But if I put both points outside, do you see where this falls apart? Maybe not. If I put C and F outside, for example, well then I also need to connect C to D, E, and F. Or sorry, D and E.
You have to go through
So if I connect it, I'm going to do this loosely first. If I connect it to D, and E, so far that's okay. So C gets all 3 utilities, but now there's no way for F to connect to both A and B. Well, actually, A fine, but B cannot, right? Now B is not going to get any whipped cream.
So you make another region.
Yeah.
You end up constructing more
Yeah.
regions.
So let's take some care and sort of do this properly. So we're really there are two cases. There's the case where we put C on the outside and the case where we put C on the inside. Let's just kind of do them both. So this is A, although they're very, very similar. A, E, D, B, and this is still region 1, this is still region 2. Okay, so case 1, put C on the outside. So C is in region 2, and case 2, C is in region 1. One of those has to be true, so okay. So we put C out here. If we put C out here, then now I will connect C to D and E. This is the kind of nicer way to do it. All right, so I connect C to D and E. But by doing that, I now create a new region. In fact, what I've done is I've sort of partitioned the outside region, region 2, into like 2 regions now. There's like region 2A or something, and now there's like region 2B. Okay, that seemed okay. But now, where do I put F? Well, now there are like sort of 3 cases, right? Where could F go? Can F go in here? No. Because if I put F in here, then C and F have to connect, and that would have to pass through either AE or AD. So that's out. What if I put F on the outside in region 2A?
Same thing.
Now F needs to connect to A and B, but now F can't get to B. So that doesn't work either. So F being on the inside doesn't work. So, all right, sad face. F being on the outside doesn't work. What if I put F in the middle in region 2B?
What if you took the D and then flipped it across?
Wait, hold on. You lost your chance to argue about the original square. It has to look like the square.
It has to be quite.
No, it's fine.
Good. Wait, one. And now if I put F in region 2B, then I need to connect to, again, now I can't get to A. So that also fails. What are you saying, Zebuda?
You flip the CD line across, so it goes around A.
No, but I think it's totally symmetric. It's like irrelevant.
Oh yeah, and then CB is a problem.
No, that's not connected to A, now it's a problem.
Okay, what's the
That
alternative?
one is being symmetric.
What's the alternative? The alternative is I put C inside, C on the inside of region 1. So this was region 1, this is region 2. So now C goes in here. This is the other case, right? If C goes in here, well now I need to connect C to D and E. So I do that. But by doing that, I partitioned this inside region into like region 1A and region 1B. And now we're going to have similar problems, because where does F go? If F goes here, then what? F needs to connect to A and B, but it can't get to B, because it's trapped inside this region 1A. Can F go here in region 1B? Also no, because then it can't get out to get to A, right? So also bad. And if F is out here, well that doesn't work either, because it can't get to C. We can't get the whipped cream to my house, because we have to pass through the quadrilaterals. Yo!
So you know, like in like the Brouwer fixed point theorem.
Wait, is this okay?
Yeah.
Yeah, I kind of want to move on. Is this like a very important? Brouwer fixed point theorem. All right, good. All right. Another graph, which is also sort of famously non-planar, is K5. And yeah, it really looks pretty non-planar, right? Yeah. All right. You could try to construct your own naive proof that this is not planar, but it starts to get pretty hard because you find yourself like stuck in some innumerable number of like weird cases. Or maybe it's not that hard. I've not actually tried recently to do this. We are not going to do this right now. This is going to be a homework problem. Yo.
Is K4 planar?
K4 is
Yeah.
planar.
Yeah.
Is it?
Yes.
Oh yeah, because you don't have to be lines.
You can just put a, or you can just put, you
I
can make
just
the
can't
lines, you
visualize.
can put a triangle with the one point in the center of the triangle.
Oh, yeah.
Oh.
Oh, yeah,
Yeah.
Yeah.
Wait.
And then put one diagonal goes around.
Yeah.
yeah, something that looks like a weird
Okay. Good. K4. Yeah, K4 is better. K5 not. All right. So what we're actually going to do on homework is actually, if someone could erase that board, that'd be awesome. What we're going to do on the homework is erase board. We are going to prove that all planar graphs have a certain mathematical property, and then as K5 does not have that property, we will have shown that K5 does not. It's easier than trying to do it by brute force. And it turns out that these two graphs, K33 and K5, are not just two graphs that are non-planar, they are like the non-planar graphs in a certain sense. And I don't feel like spending too much time on this because I'm not going to prove any of this at all, so maybe I'll kind of like do it later because it's a little bit boring. But basically, there is a theorem, and it's called Kuratowski's theorem. Kuratowski. I think I've spelled this correctly. Which says that basically, Kuratowski's theorem says that every non-planar graph has hidden inside of it some kind of K33 or K5 subgraph. Doesn't exactly say that because you have to add a couple of extra qualifiers, but loosely speaking, Kuratowski's theorem says every non-planar subgraph has a K5 or a K33 hiding inside of it. In particular, what we have to do is we have to kind of like blow off all of these like weird cases in which there's like dots there that don't belong. So like imagine you had some graph like that looked like this, right? We can make this graph sort of more annoying by adding little pit stops along the way. In fact, Gossett kind of does a whole development which explains this properly, so I'll just leave it for you to read. But if you have some graph which is just two vertices and just an edge between them, right? He calls this an elementary subdivision. If instead of going directly from V1 to V2, you like stop along the way at like some other spot, and now there's like this new like point like A. Okay, so you haven't like fundamentally altered the structure of the graph in terms of which vertices are adjacent to each other in a loose sense of adjacent. I can still get from V1 to V2, but now I have to do it via two steps. Do you guys like feel how these are like fundamentally structurally kind of like similar?
Only if A's only members are V1.
Yes. Yep. A is like a little like point that pits up along the way. Yeah. Yeah. Okay. So yeah, instead of communicating directly with your friend, you now do it via like email or something. You drop off your messages at a spot and you pick them up later. Don't say anything. Good. So that's called an elementary subdivision. Well, you can think of a graph as giving rise to new graphs, which occur by like performing elementary subdivisions on them. So like, you know, something like that. Does everyone agree that this graph is just the result of performing elementary subdivisions sequentially on the edges of this graph? Okay, so I will call this graph a descendant of this graph, and I will call this graph an ancestor. Okay, you can read about this all later. So basically, two graphs are, he says, homeomorphic if they have a common ancestor, which they can be derived from by a sequence of elementary subdivisions, which is a kind of a way of saying they're loosely sort of the same graph, basically. And the actual theorem, Kuratowski's theorem, says that every non-planar graph is homeomorphic, has a subgraph which is homeomorphic to K5 or K33. Homeomorphic. It's a new word I just defined, but maybe you weren't paying attention. Let's move on, because this is not the cool thing. Should we do the cool thing? I think it's time for the cool thing. All right, the cool thing is we have these things called polyhedra. What are polyhedra? They're like 3D polygons, Aditi Shetty. You are exactly correct. And I spent many hours this week staring at polyhedra on the internet because I'm going to buy lots of cool shapes. It's a whole new world that's opened up just in the last.
Because we made them in 8th grade and I still have mine.
You made it how?
Oh yeah, but out of like, I don't know, mine's been out of.
Like
yeah,
cardboard.
Cardboard. No. Cardboard and duct tape is like 80s.
No, it's
3D
really
printing, Aditi Shetty. This is the future. Apparently you can 3D print all kinds of cool, pretty shapes, and I shall have them after I pick which ones. Wait, maybe your polyhedra is also cool. What, do you still have it at home?
Yeah.
Can you bring it in next class?
Actually, my mom had it printed out.
All right. If Aditi Shetty's mom did not throw out her beautiful 8th grade cardboard and tape polyhedra, maybe we'll see it. All right. What are the polyhedra? They're 3D polygons. I could give a technical definition. I will not. There's a famous theorem called Euler's formula. Euler's identity, Euler's formula, Euler's formula?
Euler's
Euler's
the identity is the other thing.
Euler's
Yeah.
conjunction.
Yeah.
Yeah, Euler's formula. Euler's conjunction. All right. Euler's formula is a formula relating the number of vertices, faces, and edges in a polyhedron. Have you heard of this before? This is like a middle school classic, but possibly not. Here's what it says. Let me make sure I get it right. It says that the number of faces in any polyhedron is the number of edges minus the number of vertices plus 2. Is that the right one? Yes. Yeah. Okay. Yeah, this is like really amazingly awesome and cool. Okay, so for example, take the cube. Nice, easy shape. All right. How many faces does a cube have? 6. How many edges does a cube have? 12. How many vertices does it have? 8. 2. Boom. Good job. Okay, that's pretty exciting. Take a tetrahedron. What am I doing? Yeah. Boom. How many faces? 4.
Oh, 4.
Yeah. 1, 2, 3, bottom. Tetra, 4. Yeah. How many edges? 6, I think. Minus vertices 4 plus 2. Again. Whoa. Okay. So this is not just true for these regular polyhedron, but it's true for all polyhedron. This is called Euler's formula. We're going to prove this in about 15 minutes. First, the Platonic solids. They are really awesome. You may have heard of them. Grab that last one, please. All right. So, we might need to go handheld with the camera. You know how to unsnap it? All right. So, welcome to the Platonic solids. You may have heard of them. They are the 5 regular polyhedra. A regular polyhedron is one in which the faces are all regular polygons, equilateral and equiangular, and also that they are consisting of only one type, and they meet, and they're also regular in the sense that the same number of them meet at each vertex. Okay, so this is a tetrahedron. It is composed of 4 equilateral triangles, with 3 of them meeting at each vertex. The cube is 6 squares, regular quadrilaterals, 3 meeting at each vertex. We also have the octahedron, which is 8 equilateral triangles with 4 meeting at each vertex. The dodecahedron, 12 regular pentagons with 3 meeting at each vertex. And the icosahedron, 20 equilateral triangles with 5 meeting at each vertex. Okay, this is awesome. Before we proceed any further, let's draw them. And by that I mean, what I want to do before you put that back, each of these regular polyhedra, in fact all polyhedra, can be drawn as a planar graph. In other words, what we want to do is we want to convert this 3D shape into a 2D shape so that we can analyze it with our modern tools of graph theory. And this can be done by, it's kind of weird, maybe you've seen this before, you take one of the faces off, like the back, and then you just kind of flatten it. Or you can think of it, if you're into that kind of thing, as the entire rest of the plane being that back face. So the so-called planar embedding of a tetrahedron is like this. I claim that this represents the tetrahedron in some kind of fundamental way. Because, after all, there are 4 vertices. There are 3, the degree of each vertex is 3. That's because there are 3 triangles meeting at each vertex. And also we have 4 faces. That's 1, that's 1, that's 1, and the 4th face is like everything else, right? So you think of that last triangle just kind of becomes like the whole outside region. Are you good? All right, good. Draw a cube. Go. Draw the planar embedding of a cube. Like actually draw it, don't just think about it. If you want to hold the cube, you can. Take the cube, take off the back face, flatten it out. Yeah, good job, Calvin. Next, octahedron.
Yeah.
K4 is by hard shape then, isn't this like K4 like this 4? No, it's not. It's not. It's like there's no line. It's also not it's not 3, it's like this one's not connected to this.
Yeah, and so for the octahedron, you have to hold it in your hand, take the back triangle, and just like kill it, and then spread out. It really helps if you're holding it, or it helps me. I find it hard.
So if you look at
Can you turn it down a little? And then a little I'm trying to look at the back face. Through. Okay, there we go. Whoa.
I'm giving it my best things.
Yeah, so you get like this reverse orientation kind of. Need 2 more on here, right?
Yeah, I don't know where they go.
I actually really like this shot.
Wait.
That's like 2 hours.
Do this again.